All right. All right. Let's go.
Okay. So question one. So we have a probability space, right? That has we want to show that the intersection of countably many sets of measure one also has measure one. Okay, so suppose you have a sequence fi, and then you know that mu fi is equal to 1, right? Now we want to find out what the measure um, of this is, right? So first thing you can do is
Oh, you
note,
wanted the intersection, right?
sorry?
You wanted the intersection.
Oh, sorry, of course. Yep, intersection I1 infinity. And so one way you can handle this is by considering the complement. So you know it's equal to 1 minus the complement of this intersection, right?
Yeah.
You know by De Morgan that that complement is equal to the union of the complements, right? And now let's just consider an arbitrary Fi. FIC has measure 1 minus mu Fi equals 0. I got this 1 because we're working in a probability space. So the measure of sigma is 1. And so you basically have you want to find out what the measure of a countable union of um mu null sets. And we know from the book that um the lemma from the book is countable union mu null is mu null. Have you guys seen the proof for that?
No.
Yeah.
Of course you did. But is everybody comfortable with this lemma, or should I explain why it's true?
And how long does it take to explain it?
I need to assume another lemma, and I think I can assume that.
Okay, go ahead.
Okay, so we need two lemmas. The first lemma is this: the union of fi is less than the measure of a union is less than the sum of the measures.
Hmm?
And then this we've seen how to prove this in Math 4001 and Math 4005. You can prove that in your own time. And then the other one is the monotone convergence theorem. So suppose you have a sequence fn going up to f, then it follows that ufn goes up to f as well, uf, right?
Okay.
Okay, so let's just define gn to be equal to what do you call it? Gn to be equal to the union of from 1 to n of fi, right? Now considering arbitrary gn, you know mu gn, mu gn, right, is less than the sum 1 to n mu of fi, right? Because of this version here, right? And so by assumption that each mu fi is 0, and so this thing here is actually just 0, and you know measures map onto the positive to the negative reals, so then you know that this is also greater than 0. So by squeeze we deduce that mu gn is equal to 0 for all n,
Okay, makes sense.
right? And it's clear to see that gn is monotonically increasing to 1 infinity fi, because when you union you can only get bigger, right? And so then it follows that mu gn converges to mu of union fi by the monotone convergence theorem, right? but we know that mu gn is always 0, right?
Yeah.
And so the only way we can avoid a contradiction is that this is also 0. And so what we've just shown is that the countable union of mu null sets is also mu null. So then going back to the main point, we can see that this is true. So this thing here is just equal to 1, which is what we wanted to show.
Nice.
Okay, so that's question 1. I'm not sure where Kay got it, but it's quite a good question, I think.
Yeah. Sign question 2 then?
Yeah, so can you guys see question 2 now?
Not on my screen, but maybe
Where did
Wait,
you guys
where-
put these questions?
This is from the problem sheet.
Yeah, I can see it now.
but where did you get the problem sheet from?
KA, do you want to tell them?
It was from different sources.
Okay, cool. Just, you know.
Yeah, I didn't bother to reference all of them.
oh no, plagiarism.
His name. What is angry? I can't remember his name though.
David Williams. Okay, here, note that this is an arbitrary intersection.
Okay, yeah.
And Abidor told me a couple days ago, now it finally makes sense. You can have uncountable intersections. That's a thing as well. And you can have uncountable index sets. Okay, so all we need to do is we just have to check, right? Okay, so we know for all I, we know that for all I in some index set, we know that the empty set is in Fi, right? Because we know that all of them are sigma algebras. And so, by definition, it follows that the intersection of Fi's also contains the empty set. That's fine. Second thing we need to check is complements. So, suppose we have A in here, right? In F.
Yeah.
That implies for all I, A is in Fi. That also implies, because each individual Fi is a sigma algebra, that for all I, AC is in Fi, and then by definition that implies AC is in the intersection of Fi. Right?
Good.
Then wait, this should not be a B. Should be a. Okay, and then now the third one, countable unions. Okay, so suppose we have a sequence. F. Wait, what's the good letter? We have a sequence GI, right? GI in the intersection of Fi that implies for all J, GI is in Fj, right? And then that implies that for all J, the countable union of GI is in Fj because each one's a sigma algebra itself. And then that implies mu GI is in the intersection of Fi. So therefore we respect all the axioms. Therefore intersection Fi is a sigma algebra itself. Okay. Okay. B. Let A be a family of sets of sigma. Show that there is a minimal sigma algebra, sigma A, containing A. Okay. So that's just showing that definition we gave is well defined. So if you remember, last week we said that we defined sigma A to be equal to the intersection. How do we define it? To be the intersection of all
My algebra is containing A.
yeah. Yes. Yeah, that makes sense. Wait, other way around, no?
And it follows from the intersection thing we kind of did.
Yeah. So then we're saying that this thing here is equal to the intersection of all sigma algebras which contain A. And I guess the only thing we need to check now is well, we know it exists, right?
Yeah,
I guess why do we know it exists?
because the whole power set is an algebra. Therefore, there's at least one that contains A that is an algebra. So it
Okay.
exists, and then show that it is clearly unique.
Yep. Should we show that's minimal first?
I mean, it's minimal
Oh.
by the way we define it. Because it's the intersection, you can only go smaller.
Right. Wait, I'm just wondering if you know something is like the minimum, do you know that does that mean it's unique? Or not?
Yeah.
I mean,
the way.
No. The thing is, I think what the question is asking is if two minimal, two like possible sigma algebras that are minimal have the same number of elements, show that they are the same. Or oh wait, does that make
His
sense?
set inclusion is anti-symmetric.
Yeah. No, sorry. Yeah, forget what I said. That doesn't make sense because it's intersection.
Okay, so what do we actually want to show? So we want to show that it exists.
What we want to show is that let F be any sigma algebra that contains A. Then we
Yeah.
want to show that sigma of A is contained in F.
Oh, wait, that's true.
Yeah, that's true. That's true.
Yeah, okay. So clearly we established that A is a subset of F, right? Because you know everything in A is in F, in all F, therefore it must be an intersection F. So therefore this exists. Is this enough? It exists.
Yeah.
Now we want to show it's minimal. So
Yeah.
suppose we have B, which contains A, and
And
B
and B
sigma
is
algebra. Then we know that B must be
Subset.
it must be the superset of this because B qualifies as one of F. So then in
Yeah.
the intersection, and then you know when you intersect it, you know you always go smaller, and so this thing must be less than B, and hence, the intersection is minimal.
Yeah.
Is that enough, or are we missing
I think
something?
that.
I think it is enough.
That's
Okay.
for that. Now you just need to show it's unique, all right?
Unique. Suppose it wasn't unique. Let's see.
You
I
can
mean,
simply
if it's
state
not
that what was
unique,
mentioned
then you have to
earlier on.
intersect them anyway.
Yeah, okay, yeah, suppose it wasn't unique. So we have like again B, which was the minimal sigma algebra. But then you know B is wait, then you know
Okay, so,
is
so
anti-symmetric.
suppose there are two minimal sigma algebras, B1 and B2,
yep, okay.
right?
Yes.
Then intersect them.
Yep.
Then you're
No,
gonna
but
get
minim-
something equal to or smaller than them. If it's smaller
Wait,
than
by-
them, then we have a contradiction, and if it's equal to them, therefore they're the same. Therefore we have uniqueness.
That's a good idea. Yeah, that should work.
By minimality, B1 is a subset of B2 and B2 is
Oh.
a subset of B1.
Even better. Even better.
By minimality. Yeah. I like that. Yeah. B2 implies B1 equals B2. Right, okay, that's pretty nice. Yeah, by minimality. Wait, so I'm just wondering, is it true to say that if something is minimal, it's unique, or that's not always true?
I don't know, because like here it's anti-symmetric.
In
Yeah,
this case, yeah, that's because.
Okay, but I
Yeah,
guess
like you
it's
said.
probably not in general. Okay, so we have omega equal to 1, 2, 3. and we want to find two sigma algebras f1 such that f1 union f2 is not sigma algebra, right?
Okay,
Um,
sure.
So I guess we know for sure that a sigma algebra must always contain empty set, and then by complements it must always contain sigma, wait, omega. And then so then let's say f1 contains 1, and then by complements it must contain 2,
2,
3.
3.
And then I think we can stop here because everything is satisfied. We don't have to check about the countable additivity because we're finite.
Yeah.
Sigma, empty set, omega, then 2, um, 2, wait, not 2, 3, it'll be 1, 3 now, right?
Yeah.
1, 3, right? So it's clear to see by checking the definition that F1 and F2 are both sigma algebras.
Yep.
And now,
But then the union has 1 and it has 2, but it doesn't have 1, 2.
exactly, yeah, exactly. So what Tiger said, 1, 2, is belongs in F1 union F2, but 1, 2 does not belong in F1 union F2. Therefore, not a sigma algebra. Okay. So this is all the easy questions. Now we will go to the hard one.
Yay.
Okay, question 3. Okay. Can you see the question?
Yep.
So I guess one thing to note is this new notation here. This new with U, it just means all possible unions of J is a sigma algebra. And then we have part 2. So let's just do part 1 first. Okay. Okay. So we have a partition. Partition Pi, right? And partitions are they satisfy 2 things. They're pairwise disjoint. That means when you intersect any 2 distinct ones, you get the empty set, and they union to give omega, right? Okay. So now we want to show that the set of all possible unions is a sigma algebra on sigma. Okay, I'm not sure about this step, but so we want to show that the empty set belongs in this thing here, right? And you can just have the union of nothing.
Yeah.
Yeah.
Union of nothing is equal to the empty set, and I can show why that's true. So suppose x was in I, so your index set here is the empty set because you have nothing. Suppose x was in I.
Didn't we do something like this in Intro to University Math?
Oh, did we?
Yeah.
Okay, but anyways, it just boils down to the fact that if x is in this, that means there exists an I in the empty set such that x is in I. But this can't happen, therefore this is false. Therefore, new Pi can't have anything, therefore it's empty. And there's also like another similar thing. I'm just gonna do it in rainbow. The intersection of nothing gives you the full set. That's similar techniques.
Okay, that's interesting. Oh wow.
So
That's controversial.
Wait, this is controversial.
No, I'm joking. I'm joking.
The rainbow or the statement? Okay, so is the first part fine? Empty set is in this new set that we described.
Yeah.
Okay. So now we want to check complements. Oh shit! Do I have to do this? Complements. Oh, okay. So proof by picture.
Ah.
Ah, yes.
Okay, yeah. This is credits to Julian, by the way.
Wait, what? Me?
Yeah, you always do proof by picture. No, I'm
Oh,
kidding.
yeah.
Okay, so we have a partition, right? And so this is just the underlying idea. So you have like these things P1, P2, P3, and then
You just take everything outside, and you're
right,
done.
and because it's a partition, right? That this thing here is actually just the union of everything else apart from P1, P2, P3. So that's like the idea, but I guess the way you write it down. So you have A, which is equal to Pi, where I is in some index set, and then so yeah, that's true. And AC is just equal to sigma minus mu Pi, right? I'm not sure if this is true, but it's just you just saying suppose I is not I1 P1, and then you can see that it's still a union of Pi. So therefore AC is still in this new set here. Is everyone happy with that? Okay. Um and now we want to show that it's closed under countable unions. Okay. So again, I think it's just like amalgamation. Like the union of unions is still a union. So you're okay. But anyway, so suppose you have like you have AI, which is equal to the union of P PIs, whatever. And then you want to union AJs. So when AJ is equal to P union of PIs, and then union of AJ is equal to the union of J union PIs. So then it's just equal to the union of J I's PI, which is still a union of PIs. Therefore, you're still in the set here, right?
Yeah.
I'm not sure if that's fine, but I think it's just purely a malinterpretation, but it's just like the underlying idea is that the union is still a union, so it should be fine. Okay. Now we're going to do part 2. Oh wait, therefore, oops, stop. This Pi is sigma algebra. Okay, so now let's go. So the converse is show sigma algebra F on a countable set is of the form P of a partition P of sigma. And it says warning converse is not true if mu is uncountable. If omega is uncountable.
Yeah,
And
because
we'll
then you
see-
have uncountable union, which
exactly
is no good
yeah.
for sigma algebras.
Yeah, bang on point. Bang on point. Okay, so we have countable omega and an associated we have a countable omega associated sigma algebra F, right? The goal of the question is we want to find a partition I such that when you do a set of all unions of Pi, you get the sigma algebra. Right? Let me just check that is the question. Yeah, okay. So I didn't come up with the proof for this myself. This is credits to Stack Exchange and Ming. Um. So okay. So
Wait, is it something to do with like taking all the intersections of each element? Like you
Oh
pick
my
an
god!
element and
How do you
then
think of that? Yeah. Okay. Yeah. You're very close. Yeah.
is that the idea? Like you pick an element and you take all the sets and intersect it, and then
Yeah.
you do this for all the elements, and you're left with a sorry, not a countable number of sets, and because all
And
of those
that's
sets are
everything.
intersections, they're kind of like they're like the simplest ones, and they can't um
Intersect.
they
Yeah.
yeah they can't intersect otherwise because otherwise they would be
What's the
included in
label?
this set of intersections we already have. I think it's something like that.
Yeah. Tiger is exactly like that.
Hey,
How do you think of it? That I did not come up with that. I had to stack exchange this.
I don't know. I kind of just thought about the picture idea, and like how you
Yeah.
want to isolate these islands. So you just intersect them until you're left with the smallest possible island.
Yeah. Exactly. So you want to find an element of sigma algebra that is that contains x in omega and what do you call it? That contains x in omega and it's minimal, right? Okay. So the way they do it on Stack Exchange is they define this set Lxy. So we first let's just fix x in omega, right? Now we define this Lxy as um it's some element in the sigma algebra a if a satisfies the following: x is in a, right, and y is not in a, right, and it returns sigma, I mean omega, otherwise, right? Um, and so the idea behind this, idea behind this is to separate elements. The idea behind this is to separate elements. So basically, for each y, you want to basically associate a that contains x, not y. So then, when you do the intersection, so let's just define Lx, which is defined to be the intersection of Lxy, um, where y is in omega. This Lx is exactly what we want, right?
Yeah.
And also, just some things to note. Do you see here the assumption that omega is countable is you really need it because we know that in sigma algebras, it follows from a lemma that countable intersections are also um, in the sigma algebra. But if omega is uncountable, then this thing is not necessarily guaranteed to be in sigma algebra.
Yep.
But okay, that's aside. So now we want to show that equal to the intersection of a's such that a is in the sigma algebra and x contains a. So this is the thing Tiger described, right? It's
Yep.
the intersection of all a's in the sigma algebra, which contain x, and so when you do this intersection, you get the minimal subset. But this is how we're going to construct it. And now we want to show that these two are indeed equal. And I guess one of the ways we know how to do that is method of inclusion both ways, right?
Wait, is it obvious to anyone that those two should be equal?
Yes, if it's obvious to anyone, please explain.
Why? What should be equal? Sorry.
These two. show like so given this definition of let me just do though. Given this definition of xy, the intersection of lxy over omega is equal to the thing Caio described. Why those two should be equal.
Wait, sorry. It's because I didn't properly catch how you defined LXY.
So it's in this piecewise function here.
Okay.
But okay, so I'm not sure if there's like a better way that's like more intuitive to show that these two are equal. But I'm going to show inclusion both ways. So suppose L is in here, right? That implies for all y in omega, right? L belongs to LXY, right? In particular, L belongs in LXL, right? Because L is in omega, and so I think we can assume that L is not equal to X, right? Because if L was equal to X, then obviously it's here, because all of these A's contain X, right? So then let's assume that L is not equal to X. So now we say that if L belongs here, then L must also belong to LXL. Then if you look at the definition of LXL, right, it's equal to A in F if X is in A and Y is not equal to A, right? So my claim is LXL cannot possibly be this, right? Does that make sense? Can someone explain why if LXL contains L, it could be the top option?
Is everyone confused?
I'm confused.
It's
Well,
it's
because it says by definition it doesn't contain L.
yeah, exactly. So if it does contain L and L is not equal to X, then it can't possibly be the first one. It has to be this one. But what that tells us, what that tells us is that for this tells us that for all A in F, right, X in A implies L is in A. Does this part make sense? This part took me a very long time to understand. But intuition that matters. But does it make sense that this is true, that this is also true?
Yeah, it kind of forms an equivalence relation.
You know, that was also the other method that people did.
That's what I'm thinking of. Yeah.
Yeah, but basically it's saying, yeah, exactly, equivalence clauses. Yeah. Oh, maybe that's a better way. Anyways, okay, let's just do this way first.
Yeah.
Yeah, because if you have an equivalence clause, then you have a partition. Oh my god. Okay, whatever.
Yeah.
But yeah, so it because what this is saying is like you can't find a set A that has X but not L, right? That's what this top part is saying. So therefore, this must be true. But then do you see that this implies that L is in this intersection of A? Because for all A and F that have X in A, then L must be in A. And so because L is in all of those A's, and it must be the intersection. So that's step one. So therefore, we conclude that xy is a subset of the intersection of A's. Is everyone happy?
Yeah.
And then, so suppose we have L in the intersection of A, A in F, X in A, right? Then this means for all A in F, X in A implies in A, right? So does this make sense? So basically any set which has X or L. Otherwise, L will not belong to the intersection because then you'll have one set which doesn't have it, and then when you intersect, it gets lost. So then that's why that's true. And then this means um, when you consider LXY, right? You know that X is in LXY, right? That's true. And so then that implies L is in LXY. So then now you have inclusion this way. Therefore, um, right. Is there any step I should go through again in case it wasn't clear?
Yeah, sorry, I'm just I'm trying this proof by myself
Yourself.
because
Yeah,
like I don't
that's
know, the
good.
way you've laid it out is a bit confusing. So
Yeah, this is
I
technical.
don't know. I'm just okay. I'm just trying to see if I can do this myself. So like the way I've done it, I've just defined the sets LX for all of the X's. Um, or the way I've done it, I've called the sets A1, A2, A3 for the elements, and I just renamed the elements 1, 2, 3 because you know it's countable. You can rename them as the natural numbers.
Yep.
And so then what I need to do is I need to show the AIs are all partition, and I have to show that um, any any set in the sigma algebra can be reached by union of AIs, which I'm trying to do now.
Okay. Fine. So keep going with that. Okay, so now we've established the properties of LX. Now the claim is that the set of LX and omega forms a partition forms a partition um forms a partition um for omega, right? So I guess we have to check the two properties. Um so property one needs to be exhaustive, right? So you want to show so first of all, clearly this is true, right? Because all of the LXs are subject of omega, right? And now we want to show well omega is equal to the union of x's, where x is an omega, and clearly that's a subset of Lx, x and omega, because each x belongs in one Lx, and so you have that omega is equal to the union of Lx, right? So that's why it's x. Now we need to show they are disjoint, right? So one way to show they are disjoint is suppose Lx intersect L is not empty, right? Wait,
Yeah.
yeah, then that implies Lx is equal to Lz. That's one way to show they are disjoint, right? Um, and so that means if it's not empty, then there exists an A um in Lx, Lz, right?
Yep.
And then that implies um in Lx. Okay, so this is the thing I wasn't really sure about, but so they said that if you have A in Lx, then this implies La is equal to Lx. Reason being, um, reason being is um by symmetry. And the symmetry is if you have you have y, a. But this part I wasn't actually really too sure about why it's completely true. So I was wondering if you guys could help.
That's the exact part which I was working on in my proof as well. That I'm a bit stuck on.
Okay, but anyways, so once you prove this, right? Then you know by transitivity of equality that LA is equal to LX is also equal to LZ, and then you're done. And then I guess you have one more thing to show about how how that the union is actually equal to F, but that's not too hard. This is the hard part here. Um, okay. So if A is an LX, then that implies LA is an LX. Hmm.
Oh wait, I think I know how to show that.
Okay.
Because if so,
Like
you
it's
want to show that.
important, right? Like because the A and X's must be together. Like
Yeah, because you can look at the
wait a
complement.
minute. Oh, okay. Wait. What?
So if A is in if X is if X being in the set implies A is in the set, then you
Yes.
can
Yes.
show that A in the set implies X is in the set by looking at the complement, because
Oh, that's how you do that. Right. Okay. Wait. So
since it's a sigma algebra.
okay. Wait. Let's just formalize that. Okay. So A in Lx implies that for all y in omega, um, wait, what does this mean again? Yeah, A is in Lya, wait, Ly, Lxy, right? That is this, because Lx is again just intersection, right? Um, and then that implies that A must belong in Lxa, right? And then we've seen before that this implies that um, for all A in F, X in A implies A in F. Wait, um, wait, can you guys hear me?
Yeah, yeah.
Everything's just going really.
Yeah.
Okay, wait, X in A implies A is in A, right? Because if A is in Lxa and A is not equal to X, then the only way this can happen is by similar reasoning. So now it's just what Simeon was saying. We need to show the other way.
Yeah.
Wait, so how the complement thing you were talking about? Can you elaborate on how that actually works? So, because if we can show X is in A if and only if A is in A, then I think it's pretty clear that LA is equal to LX.
Yeah. So I think we want to do a proof by contradiction,
Okay, right.
and we can. So what we want to prove is A in A implies X is in A.
Yeah, okay. So A,
So to contradict that, we would need to find a set where A is in A but X is not in A. That would be the contradiction.
okay.
I
Wait,
mean, that would be the negation, sorry. And we
Also-
want to show that leads to a contradiction.
so you want to find wait, sorry. You want to find a set A, find A such that A is in A and
But-
is not in A.
And that will lead to a contradiction.
Right, okay.
And the contradiction is of this set is in the sigma algebra. And the complement of this set contains X but does not contain A. But we've already shown that containing X
Oh
implies
my
you
God.
contain A,
Wow. Wow. Oh wait, yeah, okay. Imply
right?
A is not an AC, but it's wow, that's amazing.
Exactly.
That's really nice. Yeah, okay. So then that means X is an A, if and only if A is an A. Right?
Yeah.
therefore, okay, so then now this is like where things go down. So therefore, we know x is in LA, right? But we know LX is minimal in containing x. Therefore, LX is less than LA, right? And we know A is in LX because LX has to have x, right? But we know again that LA is minimal, therefore LA is less than LX, which implies LA equal LX, right? So then now we've shown, therefore, this LX here is a partition, right? And I guess now the last part is show this is indeed equal to f. So my claim is suppose so fix a and f, right? Then my claim is that a is equal to the union of x. Wait, a is equal to the union of b in Lx such that oh wait, no, that's not what I want. I want to say that a is equal to the union of x in a Lx, right? Because what we've said is like we've basically broken down f into like these tiny islands as Tiger like mentioned. And so then when you union these islands, which a must have, then you know you must get a. The islands of all the points that a has. I guess, is there a better way to do this apart from inclusion both ways? Or should I?
One way is obvious, right?
Yeah. Well, obviously, clearly A is a subset of this. Now we want to show the other way. Wait. Oh wait. Because so suppose we have L in this union Lx, right? Then we know L must equal must L must belong to some Lx, right? And we know that L is an Lx implies wait. Oh wait, we know that if L is in Lx, then that means X is in A if and only if L is in A, right? Therefore, because we know X is in A, then it follows that L must be also in A. And hence, this is true. I think that works. What do you guys think? Wait, can you guys hear me?
Yeah.
Yeah.
Okay, so is this fine? Also, I think Simeon's way, where he said just consider an equivalence relation, that would probably be much nicer.
I mean,
Because
that's like kind of the way I thought of it, but then you still have to prove that you still have to prove that any set in the sigma algebra can be is a union of this partition.
all right, yeah, but I think this is how you do it. So clearly, wait, you can't see anything. Clearly, this is true here, right? And then this part here, is the one that needs a bit more work because I guess it's this statement here that we proved before. Not sure, but I think this is true.
Wait, I think there's a slightly better way. Slightly.
Yeah, go on.
Like, you want to show that the union is in A, so for each x in A, you want to show that Lx is in A, right?
So wait for all. Say that again. So for all
X in A,
Yep. Okay.
you want to show that L X is a subset of A, right?
Yes.
And if you look at the formula for Lx
Yes.
up there, if you look at the one on the right, A is in that intersection. So it's a subset of A.
Okay. Wait, sorry, I didn't actually fully catch that. Wait, where
So if you scroll to the definition of L,
LX?
yeah, Lx, and you look at the second inequality, then A is in
Oh,
one of
here. Yeah. Okay. Yeah. Oh, you mean this? Wait, you mean with this inequality or this one or this one?
I can't actually see anything.
Oh wait, is it black again?
Wait, no, it's frozen for me.
Oh wait, how is it for everybody else?
Oh wait, actually, yeah.
Oh, it's fine now. Yeah, it
Now
just
it's
switched.
fine.
Okay, that's probably my internet connection. So I guess you want to show that if L isn't A, then it's a subset. Oh, you want to show this way, right?
If you use the definition, like Lx, like above, like at the topmost,
Yeah.
the topmost equation, yeah, use the definition of Lx on the right.
Okay.
Like the intersection of A and F, such that
Oh right.
wait, that one.
Yep. Okay. And then I guess if we scroll back down, we want to show.
So X is in A, therefore, Lx, if you look at that definition, is a subset of A.
Oh wait, because it's sorry, because this LX is an intersection of A. Yeah, okay, fine. Yep. Does that make sense for everybody else? But I think that's fine. You can read. I'll try post these notes. Then you can read through them again.
Very
If
good. Take them.
now, you guys want to do more questions, or should we call it a day? I think we're halfway through actually.
We can. I don't mind either way, but if we are going to call it a day, then I have one more question to add to it. I'm going to quickly post in the group chat.
Okay.
Either in the group chat or in the Discord, whichever one you prefer.
I think Discord.
Yeah.
Yeah,
I'll
so
post
I
the question.
assume we're just gonna be like mainly using Discord, this Discord now instead of like the last one we were using.
Yeah.
Oh yeah, and for the next week, I would want people to look at limit superior and limit inferior for sequences, lim sub and lim myth.
Didn't we do that in analysis already?
Yeah, we've done
Both
that.
of you
It might be worthwhile to relook through them.
Okay.
Wait, so does anybody else want to do more questions? Because the later questions actually talk about some of the more difficult stuff. I think everything so far, 1, 2, and 3 are stuff that realistically you could have done in Math 4005, but like 4, 5, and 6 you couldn't have done.
I can do 4 and 6, but I'm not sure about 5 because I can only show
5
one
is-
way.
Yeah, like no, I can't even show it anyway because like so first it's defined on algebra. Like we have
Yeah.
the one. So like one way would be trivial under monotone convergence theorem, right?
Yeah.
Monotone convergence theorem assumes you're working on the sigma algebra.
Yeah,
So-
but I don't use monotone convergence sequence as a theorem. I assume the sequence so whenever a series is finite, series converges, then it is Cauchy, that means tail goes to 0. I used that one to show one of them. I can show the other one.
Oh wow. Okay, that sounds more like what you should probably be doing as opposed to just porting one from convergence. Okay. But okay, wait. Do you guys want to do 4, 5, 6, or should we just call it a day? What are people feeling? I'm happy.
I don't mind.
I can keep going.
Yeah. Okay.
Yeah, I probably have to go soon.
Yeah. Okay. Just drop out when you need to. I guess.
And of course, this thing, I'm recording it on my side, so you can always come back and review that if you want.
Okay.
Oh yeah,
thanks.
thank you, Tiger.
No problem.
Let's do pi system. Yeah, so this thing confused me, but like eventually it's just boiled down to so T is the set of all open subsets. Okay, so T is the set of all open subsets, and pi r is the pi system, which is defined to be the set of all of these kind of intervals. All of these kind of intervals. Does anybody remember what the definition for pi system is?
That's closed on the intersection.
Yeah, close. Yeah. Oh, actually, I think that probably might be better. Yeah, close under intersection. But then that implies close under finite intersection by induction.
Yeah.
Okay. So now we want to show that the Borel sigma algebra of R, which is defined to be the sigma of T, is equal to the sigma of pi R. Okay. Yep. So I guess way to do that is solution both ways. So I didn't actually use the hint, but maybe that might be the reason why my answer is wrong. But anyway, so what I said is, this is basically the gist of it. I said T is a subset of sigma pi r, right? And then, wait, K, is this true? Then that follows that this is also true?
Wait, I can't see what I've written yet.
Oh, would you?
Not yet.
Okay.
Okay. Tau is in sigma of pi system, implies sigma of tau is in sigma of pi system.
Wait,
Yeah,
is that tau?
is-
I think that's just a normal T.
Is a T, sorry. I don't know how to write it. But is this true? Is this because I think
It should be, isn't it?
yeah, because like your sigma, yeah, because the sigma,
Yeah, it should be.
right? And then what about this last thing here? Is this also true? Because like this is the most efficient sigma algebra, so when you try to find the most efficient of that, you just get itself.
Sigma of sigma algebra seems about right.
Of
Okay.
course, right?
Okay, so now we just want to show, so we want to show that every open set, right? Every open set, oh my god, I did use the hint, okay. Right. Ah, okay, no wonder. I was asking in the group chat with Simeon.
Yeah.
Do you remember how I was asking in the group chat yesterday? It's like, can every open subset, every open set of R can be represented as like the countable unit open intervals?
Oh yeah, yeah.
It was a hint. Oh my god. Okay, now that we can assume that's really easy. Okay. I'm still probably read the hint. Okay. So we want to show. So I guess Walog, right? Walog, you want to show that any open interval, belongs in this pi r, sigma pi r, right? And then because you know you're working in a sigma algebra, countable unions of open intervals just gives you it's still in the sigma algebra, right? So then we just need to show that an arbitrary open interval belongs in sigma pi r. Okay, so I can't remember how I completely constructed it. Okay, so first note that, so what the stuff that lives in here looks like this, right? So these sort of objects live in pi r, and then because now we've taken the sigma pi r, we know that we also have um we also have the complements, and the complement of this would look like this, right?
Yeah.
Okay. And then now we're going to use countable additivity, or I guess sigma additivity, right? So we know that this thing here belongs in the sigma algebra, which is when you union for n and n, right? And then this is just equal to this, right?
Yeah.
Because I think this is true. Maybe you can just like do inclusion both ways, but I think it's intuitive enough. And so now we know we have objects of this form and we have objects of this form. So now we also know that in sigma algebras we're allowed to union, right? And so you get this, right? So now you know that this also belongs to the sigma algebra. And then when you take the complement of this, then you just get the closed set, AB,
Yep.
right? And then how did the rest go? Now that we have the closed set, we want to be able to construct a B. Oh, yeah, okay, that's easy. Because, so we know that we have this. This exists in our sigma algebra, right? Now we want to show that this also exists in our sigma algebra. And then the idea is to union them and then take the complement, and then that gives you AB. Does that make sense? And the way we can make this interval here, right, it's equal to b plus 1, because we know we can construct any closed interval, union um, b plus 1 this. And then you know that you can construct this using the complement of what's the complement of minus infinity b plus 1, right? And so we've just um, shown all open intervals belong in sigma pi r. And then because of the hint, we know that all open subsets, right?
Oh, yeah,
all
yeah.
open subsets of R are just basically countable units of open intervals. But you know, because you're working in a sigma algebra, that countable
Yeah.
and are still in sigma algebra. So then that's that part. Now we want to show, and so then that yields that the sigma
Yields.
is a subset of this. Now, same idea. We want to show that pi r is a subset of sigma t.
Sigma
Right?
pi r. Yeah.
Yeah. So, no, I'm just this way first. Just this way first. So we're gonna take an arbitrary interval like this, and now we want to find out how can we construct this using what do you call it? That's
Unions of
wait,
sigma t.
this is a open interval. Wait, this so if this is an open interval, then because you know you work in the sigma algebra, you know that its complement must also exist, and so this is true. Therefore, sigma pi r, using similar reasoning above, is a subset of that. Therefore, we have equality. Is that fine?
Yep.
Okay. I should have definitely read the hint.
Yeah, it is fine. There's slightly more efficient way that's in our
Okay.
book, page 17, if anyone is interested.
Okay. Actually, I'd be interested. I spent way too long trying to figure out how. Like this part here, the second one was really easy. But the first part took me like some play arounds to work out. Did you say page 17
Yeah, page 17.
of probability with martingales?
Yeah, 1/7. Yeah.
Okay, I don't actually know how to do 5. But I'll just write down the question. Oh, and also 6 actually really boring.
Yeah, 6 is easy.
Yeah. I wrote down an example beforehand, and I can just paste that on so you guys can read that. Okay, will you be up for tackling question 5? I'm not sure how many hours it will take though.
I can only do I can
One
only
way.
do one implication. I can't do both of them.
Okay. And then let me just sort out question 6.
Okay, which implication can you do? Which one can't you do?
So so when you assume that every sequence of A with an goes to 0, mu of an goes to 0, that implies. So I can't do the. So I'll call those two parts before if and only if and after if and only if as part 1 and part 2. I can do part 1 implies part 2, but not part 2 implies part 1.
Part 2 implies part 1. Oh, actually, it's not too bad. So, I think I can do it.
Okay then. Let's have Ming do it.
Wait, what?
Wait, do you have a graphic tablet by any chance?
Nope.
Oh, wait,
Nope. I mean, I can just
KA,
say it.
you know you can collaborate on this? You can write on this if you have your graphics tablet with you actually.
Yeah, but I haven't got the software.
Oh, it's by the way, it's free on Microsoft, by the way. Just takes like 3 minutes to download though.
But what software are you guys using to write all this out?
This is Microsoft Whiteboard.
Oh, okay.
Also, by the way, Tiger, I think it's you know your tablet. I think it's possible to stream on it actually.
I mean, I'm thinking I can just screen share from my tablet, like if I call on Discord, but I don't really
Oh,
want
right,
to do that
yeah.
because I can't record that at like
Yeah.
the same time. So
Okay. So this is part 6. It's literally find examples. So, a system is just something that's closed under finite intersection, and so it says what happens if you don't assume it's a pi system. And so clearly this thing here is not a pi system, right? Because intersect you get 2, but it's not an I. And then you just define these measures, and then obviously they don't always agree on F, so you have a contradiction. But that's pretty much it. It's just literally find an example. So 5. Okay.
Wait, so 2 implies 1, right?
Yes.
So 1. Okay, so we're assuming that for every decreasing sequence of sets, decreasing to the empty set, that mu of an goes to 0.
Yeah.
Okay, then you want to show it's countably additive, so let a1, a2, so on be disjoint
Yes.
sets. Okay, and then what is mu of the union?
Mu of union would be the entirety. Yeah, that falls. Let's say that A.
Wait, yeah, mu of the union. So you can like decompose it into a finite union and some infinite union.
Yeah.
Okay, so
Wait. So what?
so
Oh,
you have
want
like
to
an
decompose.
you have an infinite union, right?
Yeah.
So take the union up to some n, for example. So the union of from I equals to 1 to n of AI.
Yeah. And then
And
union that
since-
to remaining.
Yeah, exactly. So you can write it as a sum of
Or unions.
two.
Yeah, I can write that as some.
Wait, is anyone writing this out?
Wait, can you answer my
bad.
friend? I have to go toilet. Sorry.
Oh, okay.
Okay.
Okay, so for the first one, you can take the sums, all right.
Yeah. So like what do you want to show?
And for the
So
for the
that-
tail,
Yeah, the tail goes to 0, right? By the assumption.
how do you know it
So
goes to 0?
So do you see that the union from I equals let's call the union from I equals to n of AI to infinity, let's call it BI. Then BI
Yeah.
is a decreasing
Yeah.
sequence, right? It
Yeah,
decreases to the
but
empty
there
set.
is why to empty set?
Why to the empty set? Let consider the intersection of the BIs.
Yeah,
You
they
want to
are
show that
all
the
empty.
intersection is empty.
Yeah,
Right.
they're already empty. Are they not? Oh no.
Wait, the intersection of BIs, you want to show that that is empty. Is because that B it's decreasing because it's subset, right? BI plus 1 is
Yeah,
a
it is a
subset of
subset.
BI.
Yeah.
Yeah, and you want to show that the intersection is the empty set. So that's all you have to show.
Wait, in order to show that tail goes to 0, you consider the intersection.
Yeah, the intersection of the BIs.
Yeah, I agree.
So do you see why it's empty?
No.
So by definition, so let X be in the intersection of the BIs from
Yeah.
I equals to 1 to infinity, for example. And then
Yeah.
so BIs by definition is a union of the tail of the AIs, right?
Yeah.
So X is in some BI.
Yeah.
So which means that X is in some AI. Because BI is the union of AIs.
Yeah.
And it's in a unique AI since they're disjoint.
Ah. Yeah, that works.
Yeah, so the tail of the BI is
yeah,
will
yeah,
contain
yeah,
X.
it goes to 0. Yeah, you were right.
Yeah. Okay, so basically
Yeah,
that's it.
That's it.
Can you explain, please?
Okay, yeah, explain.
Wait, can we?
Okay.
Wait, which direction do you guys want to do first?
Let's do 2 implies 1 first.
So this way.
Yeah.
Okay, let me stick with this.
So you are assuming it's additive, and you assume that for every sequence of an goes to mu of an goes to 0 whenever it is decreasing to empty set.
Right. Also, I was just wondering. Here, this. You know how it's not a down arrow anymore? It's just this. Is that a crucial fact, or that?
Where?
Here. You know how it says mu an converges to 0 as opposed to monotonically?
Oh yeah, it doesn't matter.
It doesn't matter. That's just okay. It's just
Yeah,
minor detail.
yeah. It is automatically monotonic based on
okay.
how it's defined.
Sure.
Or maybe not.
So let's go this way.
Okay, so consider some disjoint consider a sequence of sets AI, those are disjoint.
We'll log this joint. Okay.
Yeah.
Sequence AI. We'll log this joint because I think in math.
Wait, not Willog, because you want to prove that
you want it to be
additive.
arbitrarily true. So consider arbitrary sequence. Arbitrarily disjoint sequence.
Wait, arbitrarily disjoint. Isn't that the same as we'll log disjoint?
No, it must be disjoint. You're not assuming it's disjoint because you want to prove that it's an additive set function. So you want your sets to be disjoint.
Okay. Yes.
Okay, so that would be, so you want to find mu of union of AI, right?
Yes.
So
Okay.
mu of union of AI is going to
Yeah.
be mu of union from I equals 1 to n of AI, union of I equals n to infinity of AI.
Oh, so
So you break them into two unions at some point.
yep. Okay. So like this.
Yeah, and due to sigma additivity, you got plus in the middle, and not due to sigma additivity, due to just the additivity.
Yes. Yep.
And now we want to show that limit n tends to infinity of the second term goes to 0.
Limit of infinity of the second term goes to 0. Yes.
That's what we want to show. So second term can be seen as a sequence that is decreasing, isn't it? When you increase n, so that is monotonically decreasing sequence, isn't it?
Yep. Okay.
So
Yes.
all we have to show is as n goes to infinity, the union goes to empty set.
Okay. Yep.
Okay, now you suppose it does not go to empty set for a contradiction.
Okay. But how does this show that it's countably additive? Or am I missing something?
Okay, so as n tends to so if n goes to infinity, left hand side equals the first term only.
Yep.
Isn't that what it means to be countably additive?
Oh wait, mu is countably additive. I thought it was the sigma. No, sorry. Okay.
Yeah, we want to prove mu is countably additive. That means we want to show that as n tends to infinity, the second term goes to 0.
Wait, let me just wait. I just need to look up the definition. Wait, so to be countably additive means that for any set AI, um, oh my God, yeah, okay, yes, yes, yes. Okay.
Yeah, we agree.
I get you now. Yeah, because I kept thinking countably additive referred to the sigma algebra, but it's not. It's
Yeah.
You said it needs to be pairwise disjoint. Oh, okay. Yeah.
So we know that thing in rainbow decreases. So if we are able to show that it decreases to empty set, then by
We're
assumption
done.
that would be 0, right?
Yes.
Okay. So suppose it does not approach to empty. It approaches to something. Suppose that's not empty set. So
Okay.
suppose it approaches to a set which contains some element, say that x.
Wait, so that this goes to
Suppose the
No,
union.
no, no. There's no mu. It's the intersection. So that down arrow means that the intersection.
Oh yeah. Let's do it in a better way. So define bi.
okay, wait, sorry, let me just get time to like grab stuff out.
Yeah.
Okay, so
Yeah, I was trying to skip it and it didn't work out. So define bi
yep, defined to be equal to this.
to be equal to I equals call that bn, please. So bn equals union of I equals n to infinity of ai.
I equals n to infinity. Okay, yes. Yes, okay.
Yeah, and bn is monotonically decreasing.
Yes, okay.
We want to show it is monotonically decreasing to 0, to empty set.
Which means that the intersection of bn's is empty.
So we want to show the intersection is empty. So if it's monotonically decreasing, it means you just take the intersection and you get the smaller one, and so on. So by definition, it is you want to show the intersection of it, intersection from n equals. So intersection of bn to be empty. So that's what you want to show.
Wait, so you want to show that the intersection of bn,
Yeah,
so from n equals 1 up to
infinity.
3 equals empty set?
Yeah.
Yep.
Okay, suppose it is not empty.
Okay.
So suppose x is in this.
Okay.
So if x is in this, that means x is in one of them. At least one of them.
Wait, all of them.
Oh yeah, x is in all of them. Anyway, yeah. X is in all of them.
So for all n, oh sorry, for all
It's,
n,
it's all of them, so it's in at least one of them.
yeah, sure, okay, yeah. So for all n, x is in Bn, okay.
Yeah, so it's in all of them. That means it is in at least one of them, right?
Yes.
Yeah, that means it is in the union. Because Bn by definition is the union of AIs, isn't it?
The
It's in some AI.
Yeah, so since it's in union, it must be in some AI.
Wait, okay, wait. Say that again. Sorry.
So since x is in Bn, so
Yes.
write the definition of Bn there. Then x is in union of I equals n to infinity of AI, right?
Yes.
Yeah, x is in union means x is in one of them, at least one of them.
Okay.
Yeah, so call that am or ak, whatever. Suppose x is in ak.
AK.
Yeah,
Can we call it K?
no, okay. Yeah, x is in ak. Since ai's were disjoint,
Yes.
that means it can't mean anything else, just in ak.
Okay.
Yeah, that
And
means
it can't
just
be in anything greater than
yeah. In particular, it can't be anything
AK.
greater than k.
Yeah, yeah.
Okay. Wait. So as AI is disjoint. Wait. Say that again. X can't belong.
So since ai's are disjoint, x can't be in anything else apart from ak. In particular, it can't be in anything in a with subscript greater than k.
Right. Okay. Wait. Let me use great. Strictly greater. Yeah. Okay. Like that.
Yeah.
Yep.
Yeah, so no matter what element you see that x, so therefore x is not in union from any.
Oh. Yeah. Nice. Okay.
Yeah, that's why it goes to 0.
Wait, Ming, did you think of this on the spot?
Yeah, he did.
I've seen something similar before.
Oh right. Okay. Fair. Yeah. Fair game. Okay. Therefore. Right.
Yeah,
So therefore Bn goes to 0. Oh, and then therefore. Oh, wait. Oh, yeah. And then I guess to hit home to like the fact that you want to show it's countably additive, right? You want
yeah,
to because you fixed n, right? You've sorry, my computer's lagging. Um, you want to show that mu of the pairwise disjoint from 1 to infinity is actually equal to the sum. Oh my god,
yeah, yeah,
sigma. Is actually equal to these,
yeah,
right? Plus
0.
this bn, and so
Take the limit on both sides.
Yeah,
as n goes to infinity, that we have
mu of bn goes to 0.
right. Nice. So therefore countably, therefore mu is countably additive.
Yeah.
Wow, that's really nice.
Okay, now let's try the other direction.
Okay, on y va. So this way. So suppose mu is countably additive.
Yeah, or sigma additive.
Yep.
So let an be arbitrary sequence of sets with an goes to an is monotonically decreasing to empty set,
Yep.
and we want to show that mu of an goes to 0.
Yes. Okay. Wait, let me just write it down. Okay.
Okay, so define Bn equals An take away An plus 1.
Okay. Wait. So Bn defined to be equal an plus 1. Yes.
Yeah. Then mu of Bn,
Yep. Is equal to n minus
mu,
a.
yeah, mu of An minus mu of An plus 1.
All right. Also, this is lemma.
Yeah. And mu of An,
Yes. Oh, hello.
yeah, I'm here.
Yes.
Okay, so mu of an equals so mu of an equals summation of I equals n to infinity.
Wait, okay, wait. So mu of a n is equal to the sum.
Yeah, equals sum from I equals n to infinity
Yes.
of mu of bi, because it is sigma finite. I mean, it is sigma additive.
Wait, let me just think about. Wait, I from n to in. Oh, because it's countably additive. Yes.
Yeah,
Wait, but how do you know that mu of an is? Oh wait, of course, because by construction.
yeah. In doing so, if you can
Right,
see here, I've already used the fact that AI goes to empty set. If AI didn't go to empty set, then this would not be true.
Wait, hold up. Um. Uh, wait, what would be the problem if something happened?
This so the last equality would not be true.
This one here.
Yeah. So I want you to draw concentric circles, like 3 or 4 concentric circles.
Okay.
Okay. Now, yeah, we call them different things. So, suppose there is suppose the last one, the innermost circle has got some positive radius.
Okay.
Yeah. So by definition, B1 is the area between the first circle and the second circle from outside, isn't it?
Is this one?
Yeah, that's B1, and another one is B2, and so on, isn't it?
Yep.
The last B1 is the area between the smallest circle and second smallest circle.
Wait, sorry, say that again. So,
So it's the last Bn.
oh yes, the last bn. Yes.
Yeah, I'm being totally unreal here. So last Bn would be the area between the second last circle and the last circle, isn't it?
Yes, that would make sense.
Yeah. If last circle is it has got some positive radius, in
Yes.
particular if that's non-empty,
Okay,
then
yeah.
isn't it obvious that it won't be An would not be all of it would be all of Bn plus something else as well, plus last circle as well.
Wait.
Those circles are AI. A1 is the first one, A2 is the second
Oh,
one.
right. Okay, wait. The full circle is. Oh, wait. Say that again. Sorry. I'm trying
Yeah.
to this.
So if the last circle is non-empty,
Yes.
then so for example the first circle would be all the I will call A1. So An would be union of B1, B2, all the way up to
Mhm.
last B plus the circle as well, isn't it? Last circle as well.
Yes, that would make sense.
Yeah. If you don't include last circle, you don't get all of A1.
Yes. Okay. Yes.
So in the same way, if last circle is not 0, then this identity that you've written there is not true.
With this one.
Yeah, that identity would not be true because we haven't taken into account of the last circle.
Okay. Sure.
Yeah, but by definition, we considered AN to be arbitrary sequence for which AN goes to empty set, so we are fine in this.
Okay. Yep.
Yeah, that was the point I was trying to make.
Okay.
Okay, now by definition, so the question says that mu is an additive function on algebra taking only finite values.
Yes.
So mu of an is finite.
Yes.
That means the thing on the right is convergent.
Okay. Oh,
Yeah.
sure.
If it is convergent, then it is Cauchy.
Okay.
That means tail is convergent.
Yep. Okay.
Therefore, mu of an as n goes to 0, as n goes to infinity is 0.
Wait. This converges. Therefore, it's Cauchy. And
Yeah.
then last one.
Last one, so mu of an as n goes to infinity is less than epsilon.
Yeah.
So limit that. limit as n tends to infinity of that would be less than epsilon.
Wait, where does that come from? Oh, wait. What you're saying, because this series converges,
Yeah.
then the sequence inside converges?
Yeah, rather than writing, so in the last step, where you've written mu as second last step, so can you replace
Yeah.
that n by 3? Write that a3, mu of a3, not mu of an, just to make
Yeah.
it clear. Yeah, and in the other side, that 3 as well. Now can you see why it's true?
Mu of A3, if this converges.
No, leave an for the last one,
Okay,
for the last line.
back.
Yeah, can you see why it is true? Oh no, you want 3 on the second last line and n on the last line.
Yeah, no, everything is deleted.
Yeah.
See if this works. So you want this? Okay. So move A3, 3. Yep, okay.
Yeah, isn't that by definition of sequence for all epsilon greater than 0, there exists some positive integer n, so that n is greater than equal to n implies that thing is less than
Yes.
epsilon.
That is true.
Yeah, that's what I've written there. I've used
Okay.
Cauchy to show that.
Right, okay, fine. Then because epsilon's arbitrary, or
Yeah,
then 0.
yeah,
Nice.
yeah. Previously, I did this proof and I thought, hold on a moment, I didn't use anywhere that an is empty, an goes to empty set. Like, it can't be right. Then I realized that in order to write that in
This
the
part
equality,
here.
yeah,
Right. Wow. Wait, I actually finished the problem sheet. Wow, nice.
yeah. Good.
Okay.
Okay, for everyone, I've posted one question in the group chat, in the Discord chat. So, so is that problem? So is that something that you guys are comfortable with, or?
Yeah, that's fine.
I think so. You just need to find the definition, right, and then just work from that.
Yeah, I think that's okay.
Okay, so that would be something that we'll be assuming in the next lecture.
Okay.
Okay, sure.
Wait, did we completely miss the complex analysis study group?
No, it's from 3. It's in 20
Oh, it's
minutes.
great. Oh my god, I need to take my nap though. Whatever, that's fine. Okay.
All right, so I'm gonna stop the recording now.
Sorry. Yeah. Okay.